Well, hello everyone, and welcome to our webinar. My name is Sharice, and I'll be your MC today. I am an AI systems and machine learning engineer at Deer, which is a biometrics identity company focused on providing identity while granting you your privacy. And we do that using your unique neurosignal. Happy to talk about that any other time. But like all of you joining us today, I'm super excited to learn more about smarter ways to possibly improve my workflow efficiency within the AI ML space. So a little bit about our host today. The organizers of this event are from Data Phoenix. Data Phoenix is a media and education initiative led by Dimitros Bodorets, focused on AI and data through over 100 webinars featuring speakers from DeepMind, UC Berkeley, NVIDIA, Databricks, and other leading companies. Data Phoenix has reached over 20,000 engineers like you and I worldwide. Its video production unit covers top conferences such as TechCrunch Disrupt, CES, the PyTorch Conference, and AI Infra Summit, which also support local AI events in San Francisco to ensure their knowledge reaches the global community. It's my honor to introduce our speaker today, Vlad Pavlov. Vlad is a senior director, AI and software engineering at PMG. Before that, he co-founded 3 startups, served as a VP engineering and CTO in 2 mid-sized companies, as well as has a background working at Microsoft and Intel. Vlad is also an open source enthusiast and a machine learning practitioner who won a few medals on CAGT competitions. Thanks again for joining us today, and I will be passing it over to Vlad.
Wonderful. Thank you so much, Sharice, and thank you so much, Data Phoenix, for inviting me to speak at this webinar. And of course, thank you so much, all of you, for joining us and participating in this event. And if possible, I would ask our friends from Data Phoenix to share the presentation that I am going to show to you, to all of you guys. And the core problem that we are trying to address, the core problem that we are trying to solve is what you are hearing from the news basically every day. AI needs more and more compute. AI needs more and more power. And people like Eric Schmidt are testifying in front of Congress. People from OpenAI keep telling everyone that, hey, the most constraining factor that we have at this point of time is lack of computers. We simply don't have enough servers. And it's not only about servers, it's also about power, it's also about electricity. And of course, there are different ways to address this problem. One of the ways would be simply to build more factories. So those factories would manufacture larger number of servers and then build larger number of data centers. And of course, build larger number of power plants. And this is all happening, of course. But this is a brute force approach. It's not super scalable. There is another approach, which is how to make our existing workflows more efficient, how to use existing workflows in a better, smarter way. And basically, this is the subject of our presentation today. Of course, I'm not saying we don't need more computers, but I'm saying in addition to getting more computers, we also should be thinking about how can we use them more efficiently. As Sharice mentioned, my name is Vlad Pavlov. I am Senior Director AI and Software Engineering at PMG. You guys probably never heard about PMG for a reason. Most of people here, I believe, are from technical industry, and we are a marketing agency. We are a marketing agency that is serving major brands, Nike, McDonald's, even Apple is our customer. We are one of the top 3 independent agencies in the United States, according to Forrester. We are one of top 5 worldwide. Under the hood, however, we are not a marketing agency. We are a software company. This is what enables us to be one of those leading organizations. About 8 years ago, the company developed a proprietary technology that powers all of the marketing workflows inside our company. Just to give you a feeling what kind of software it is, last year, our technology enabled ad delivery to over 1 billion consumers worldwide. Basically, 20% of the adults of the planet were touched by our technology. However, the project I'm going to talk today is my side, my personal project. It doesn't really, it's not really related to my PhD work. And I started working on this project long ago when I was participating in data science competitions. I became very excited about data science competition during the COVID time when everyone had a little bit of extra time, and I started playing there, won a few medals on Kaggle. And when you start doing those data science competitions, you quickly realize that the right strategy to win the competition is to have as many experiments as possible, to over or out experiment your competitors. And that requires a lot of compute. You spend a lot of money basically either on AWS, and that requires a lot of your personal time. You just sit and wait for the next model to get trained, then you play with that model, and then you figure out, okay, this is my next step. So this is very resource-consuming process, and this is when I started working on this small library that helped me to become more efficient in participating in competitions. And now, when the entire world needs more and more compute, but just on a different scale, because we're talking about training models that require dozens of thousands of computers that are working for months. Obviously, even if you can get 30% saving or 50% saving, this is already a huge deal. So I figured, hey, those ideas which I used at that point of time, they're even more relevant now. And that's what I'm going to be talking today. And hopefully I will inspire you to apply some of those ideas in your daily work. And this is the agenda for today. The first two parts are going to be the longest. We will talk about two core ideas that we basically can spy on the nature, see what nature does in order to be efficient, and see how we can apply those ideas in our Python-based workflows. So we'll talk about those ideas, then we will go through a couple of demos to illustrate those ideas. And then three other items in the agenda, they're going to be a bit shorter. We'll talk about why specifically functional programming becomes even more relevant in today's world and how it is evolving over time. We will have one more smaller demo, and we will talk about practical steps that each of you can take to apply those ideas in your daily work. So before we go to that conversation, let's see how well we are familiar with biology. Artificial intelligence is supposed to, well, reproduce using computers, something that we see in the nature. Neural networks in our computers are supposed to replicate what is happening in our brain. Let's talk about a biological neuron. Let's see how fast it is. Specifically, I have a question for you. How frequently does a human neuron fire? How many times a second, for example? Put your answers in the chat. How frequently does a human neuron fire? How many times a second, an hour, a millisecond, whatever you believe the right measurement. Please don't Google it, don't ChatGPT it. If you know the answer, wonderful. If you don't know the answer, just guess. Just try to use common sense. I hope everyone who wanted to do it already did it. So one human neuron in our brain, fires on average once every 6-7 seconds. I'm a mathematician by background. I studied applied mathematics. To me, it was a revelation. Our brain is actually very slow, yet it's super efficient. Let's compare human cortex with the top-of-the-line server. The server, the configuration you see on the screen, costs about $500,000. This is the best you can buy at this point of time. It has 8 top-of-the-line GPUs from NVIDIA. So let's compare it and our cortex. And of course, humans are still way more efficient than computers. So this top-of-the-line server is going to be 1,000 times faster in terms of number of operations per second. 1,000 times faster than human cortex. Yet the human brain has 20 times more memory than that top-of-the-line computer. And of course, a human brain is 1,000 times more efficient in terms of power consumed, but that's not the point of today's presentation. The point is our brains are slow, but they have a lot of memory. Modern computers are fast, but they have small amount of memory. And somehow brains are more efficient. We are smarter, at least for now, than servers. So somehow the nature figured how to replace compute or substitute compute with memory, with storage. Maybe we should spy on nature and maybe we should do something similar. And basically this is where functional programming comes in play. Because functional programming encourages people to use what is called pure functions. Pure functions have two main qualities. Number one, a pure function does not have side effects. Number two, for the same inputs, there always will be the same output, which means we can use this property of pure functions called referential transparency. In a code, inside a code, we can actually replace a call to a function with the value that it returns with these specific parameters. That leads to huge number of optimizations. And all those optimizations are based on the same idea that we just discussed, replacing compute with memory. And most of the time, it is done through so-called memoization. And for example, in Python, there is even a standard decorator that you can use. It comes with functools, I believe, that you can apply to your functions that will cache the output of the function. The first time it is called with some specific parameters, it's going to be computed. The second time the function is called with some specific parameters, it's not computed anymore. Why? Because the first time when it was computed, the output was stored in RAM, in memory. And then the second time you compute this function, instead of calling the function, the result is taken from RAM. Now, here is the problem. RAM is going to become clean once you restart your program or you restart your computer. So yes, this technique allows you to optimize your programs, but only to some extent. But what if, just imagine, what if somewhere on this planet there was this global persistent cache that stores all the outputs of all the functions ever computed by our civilization? And by functions, I mean pure functions. So the first time inside my program, I run some function with some inputs and no one else on the planet did it before, it gets computed, the results is stored somewhere forever. Half a year later, Sharice runs her program, a different program, but inside that program, there is the same function with the same inputs. In this case, there is no need to recompute this function. The result is taken from that global cache. So we did some basic modeling, and it allows for enormous optimizations in terms of speed up, in terms of making our compute faster. Depending on the size of this cache, if we are talking about global cache, what I just described, when we turn the entire computer, the entire planet into giant persistent cache. In this case, all those long-running workflows, which sometimes run for weeks and months and sometimes require thousands of computers, then can become, on average, 3.5 times faster, which is going to be huge optimization, huge speed up for our civilization. And you're going to say, come on, Vlad, it's not realistic. It's not going to happen. Most of the compute happens where? Inside the enterprise. Why would enterprise allow to take their data to some centralized place? This is the most important asset they have, their data, the new oil, their intellectual property, right? And of course, I will agree with you. No way enterprise is going to allow their data to be stored somewhere, except for 15 years ago, if someone told you, hey, in 2025, all the source code on the planet is going to be stored in one place. You would say, no, there is no way enterprise would allow to store their source code, the most precious asset, in one place where technically someone can steal it. Yet today, 99% of the code is hosted on GitHub, right? So I can easily imagine how 10 years from now, 20 years from now, there will be kind of GitHub 2.0, where the source code will be stored together with all the outputs of all the possible computations based on all the possible inputs that were provided to that source code. Again, we are not talking about all code, we are talking about pure functions, which is obviously not all possible algorithms, not also all possible codes, but substantial part of the today's code base is like this. But let's be realistic. Let's talk about what is possible today. And today, of course, we should be talking about engineering level optimizations, not global level optimizations. And when it comes to global level optimizations, that was amazing. But realistically, let's talk about enterprise. Let's talk about teams. Let's talk about companies. If I create a company level cache, that itself is going to get me at least 2x optimization when I'm talking about long running workflows, which by itself is a big deal. So from practical standpoint, we are focusing on the team level, even though big dream is global level. But from practical standpoint, for now, we are talking about optimizations that can help our teams. Of course, we can also benefit from those optimizations on the individual level, but it's less interesting. So the first idea that we are taking from the nature is replacing compute with storage. The second idea that we are taking from the nature is using underutilized hardware. Basically, an example is people sleeping. We spend almost 30% of our time kind of doing nothing. And yet, our brain is working very hard when we are sleeping. It is optimizing all the memories, it's aggregating the knowledge, it's actually even learning because we kind of create those simulated environments in our brains, and then the reinforcement learning happens inside those simulated environments. It's happening under the hood. It's happening when the brain is technically not working. So can we use computers when they're not working? And that leads us to the next question. How frequently are computers not working? What is an average utilization rate for computers? Specifically, let's talk about enterprise. It's a very well-researched subject. There is like dozens of reports about it. What is an average utilization rate for servers in the enterprise? If you know the answer, please write it in the chat. If you don't know the answer, just guess, just use common sense. What is an average utilization rate for enterprise servers? And the right answer is well below 30%. Depending on what kind of companies we are talking about, the larger the company, the higher it's going to be. For hyperscalers, it's probably closer to 50% or maybe like 45%. For smaller companies, it's by smaller companies, I mean not Google scale, not AWS scale. For them, it's closer to even 20%. So 70% of the time, the servers are sitting basically doing nothing. So if we had a way to use those servers while they're doing nothing, similarly to how we are using our brains when we are sleeping, that would actually mean tripling the server fleet for an enterprise without investing more money into hardware. Let's take it to the next step, to the next level. So we were talking about enterprise level. What about global level? Even in the enterprise, there are desktop computers, there are laptops, but all of us are also having our personal devices. Most of the time, they're not used, right? For example, in my family, I have like 6 or 7 different laptops. At this point of time, none of them is used. On average, how many do you think? What's estimate? Again, I'm asking to guess. What is an average number of computers, proper computers, GPU-equipped computers on the planet at any point of time, the computers that are sitting doing nothing, just idle? Just guess, what is the number? And the right answer is about 2 billion GPU-equipped computers. I'm not even talking about smartphones, which are also super efficient these days. I'm talking about proper computers. And of course, you can say, yes, theoretically, it would be wonderful to use them, but practically, those GPUs are very small comparing to those top-of-the-line servers, and I agree with you, but the scale is huge. So if we had a technology that would allow us to use, say, even 5% of those globally available computers, that would also speed up the workflows important for our civilization in a very, very efficient way. But again, and yes, actually, it's close to 2 billion. It's not exactly 2 billion. It's 1 billion.93 as of the first quarter of this year. Probably now, when we have the third quarter, this number is probably larger. But let's be practical. Let's not dream about something that is hard to do today. Let's be practical and talk about enterprise. Even in the enterprise, as we discussed, even the servers, which are very easy to control, there are about 50 million servers at any point of time which are sitting doing nothing. 70%, more than 70%, in fact, of server capacity can be used if we were able to, if there was a technology that would allow to easily do it. Now, again, we are coming back to functional programming, because there is one more property of pure functions. That property is rarely talked about, which is when you work with pure functions, you can achieve deterministic parallelization. Parallelizing algorithms, making them run off many computers, different parts of algorithms running on different computers, is actually hard. You need to synchronize. You don't know in which sequence those steps will be performed on different computers. You need to deal with all those race conditions, etc., etc. There are no race conditions when you're working with pure functions. None. Doesn't matter what is the sequence, the sequence of those parallelized steps, the result is always going to be the same, which makes it way more easy to parallelize your algorithms over a large number of computers. And the best technologies currently available to parallelize your algorithms, they allow to work with tens of thousands of computers in a cluster. Even that is extremely challenging today. But if you are taking this approach of using functional programming, of using pure functions, we can easily scale our parallelized algorithms to millions of computers. Let's see in practice how it can work. And I'm going to use the library that I mentioned before, the library which I started working on during the COVID time and was kind of slowly evolving. You can later play with this library, or you can do something yourself. I'm just using it now for the purpose of illustration. And the demo that you're going to see, this demo is available on Colab. You can play with it later. The link to the presentation is going to be shared after the webinar, so you'll be able to go to the presentation and open those demos, because links to the demos are inside the slides. But for now, let's look at the screen, and please do not read the explanations. You can read them later. For now, just listen to me and look at the code. So we are installing Pythagoras. We are doing the imports. And then the first thing we are doing is we are connecting our program to a portal. A portal is a storage, just a storage. But a portal is also kind of window through which Pythagoras-enabled programs communicate with each other through time and space. It's a backend, but it's a passive backend. It's just a storage. In this example, it's just a folder. So when we do our persistent memoization, the cached results are going to be stored in this folder. But it can be a folder on one computer, which is the case right now. It can also be a folder shared across several computers using Dropbox or using NFS. NFS allows you to have up to 25,000 clients connecting to the same folder. So we can easily have kind of cluster with 25,000 computers, but reality is all of them just connect to the storage. All of them are using the same shared cache. And now we are going to create the expensive function. Expensive because it's supposed to run for 5 seconds. Inside of this function, there is literally nothing right now. But in real life, of course, we are talking a function that is doing some kind of training, some kind of expensive computation, requires probably GPU, and maybe runs more than 5 seconds. this is very simple function. Pythagoras offers decorator called pure. We apply this decorator. Now we can use all the benefits of Pythagoras. And of course, the function has to be pure in terms of the way it behaves. And also it has to be autonomous, meaning you can see the imports that this function requires are inside the function. Why? Later we are going to be talking, we don't know in advance on which computer this function is going to be executed. So everything that the function needs has to be inside the function. Because of that, we are doing the imports inside the function. Other than that, we can basically be doing anything. And when we run this function for the first time, of course, it's going to, well, spend some time computing, and then it will return some silly result. The next time we are calling the same function, the result is immediately available. You see, it was very fast to get this result. Why? Because it was restored from a cache. Now, when we call this function from another with another set of arguments, well, it takes some time to compute it. But the second time we call this function with exactly the same inputs, the result is available immediately. But what if we change the source code? It happens all the time, right? People play with their code, people refactor the code, people modify the algorithms. So we change the code, and now we are calling the function. The name of the function is the same, but the body has changed. We are calling this function with the same inputs, and now it has to recompute again because the inputs have changed. But the next time we are calling this updated function with the same inputs, now the result is available immediately. But it is smart. If we go back to the previous version of the source code and call the function with the same inputs again, now it knows that for the previous version of the source code, the results are already in the cache. So it reuses the results which were computed before. And it's smart enough if we make some changes to the source code, which are just cosmetic. In this example, I added a docstring, and I added some comments and I changed formatting. But this is exactly the same version of the function that we used the first time. So Pythagoras is smart. And when we use this updated version of the function with the argument, the inputs that the function saw before, the results are available immediately. And for a portal, there is this method called describe that shows us what is happening inside the portal. There are only a few data points which are important for us right now. First, it's just a directory. As I said, it's just a storage where the intermediate results are cached. In this case, it's a folder, but it could easily be an NFS folder, or if you're using Amazon, it could easily be EFS, Elastic File System by AWS. Or if tens of thousands of computers in a cluster is not enough for you, you want hundreds of thousands or millions, it can easily be S3. So we can scale basically in an unlimited way. It's a backend, but it's very cheap, passive backend. Each of the computers that are connected to this portal, they don't know anything about all the other computers connected to this portal. We can see that right now in the portal, we have stored 3 execution results of function calls. And we can see that the total number of values that are stored is actually way larger. Why? Because we are taking this approach of immutable data. So every time there is some new data point, it is stored in the portal. It is stored basically forever. And even a function is data, all the inputs to the functions are data, etc., etc. All of them are stored there persistently forever. And the beauty of this approach is that the more computers or the more programs are connected to the same portal, the larger the cache becomes, the better the hit rate, the better the acceleration that each individual program is going to get. It's very similar to social network. The more people are connected to the same social network, the larger the value each of them gets. So basically, that was the first demo about persistent memoization. Now let's talk about deterministic parallelization, the second demo. And I'm going to do basically exactly the same. I am installing Pythagoras, which I already did because it's going to take a little bit of time. I'm doing the imports. I am creating the portal. Now, during the previous demo, when I told you that a portal is just a storage, it was half-truth. there is the other side of this coin. Let's take a look at the output of our describe method. Let's take a look at the last line. Not only we connected to a folder, but the program also launched 3 background workers. These background workers, they run in background. They're doing literally nothing. You don't see them. Every program that connects to a portal launches a few background workers on that computer where that instance of the program runs. Each of the workers is constantly looking at the portal. Each of the workers tries to find if there is a work for it to do. Instead of executing a code inside your program, you can just place an execution request into the portal and wait for some background workers, which may run on this computer or may run on some other computer. Just wait for some background worker to execute this code. And the way it works, the number of background workers that are launched depends on the available resources on your computer. If you have a lot of unused memory, if you have a lot of unused CPU capacity, the number of background workers is going to be larger. Let's see how it works in practice. We create basically the same dummy function, and when we execute this function, of course, it takes 5 seconds to run. But now we can play with a method called swarm. With the method called swarm. Method swarm is very similar to other asynchronous ways to call functions in other libraries, which is it's going to place an execution request into the portal and return an address of the future result. And after that, we can check whether the result is available for us to use by calling the function called ready. Let's do it. Let's call this thing, and now let's call ready, and of course ready returns false because we just placed this execution request, and maybe, hopefully, some of the background workers will do something about it. And while we were talking, I hope, let's see if it worked. Yes, some of the workers, actually, while we were talking, some of the workers already took care of this execution request, and now we can use the get method to see what was the result of the computation. And the beauty here is this result of the computation is going to stay in persistent cache forever. So no one is going to spend more time or power calling this function with exactly the same inputs again. And let's look at what is happening inside our portal. As expected, now we have 2 cached execution results stored, and we still have 3 background workers running, and the execution queue is empty because the only request which was there was already processed. Let's see how we can extend this model. We don't know in advance on which computer the function is going to be executed. And sometimes the computer is not good enough to execute a function. So Pythagoras often offers a concept called prevalidators. When a background worker, tries to execute some code first, it checks prevalidators. If they are all returning true, in this case, the execution request will be executed on this computer. If not, well, then some other worker will try. In this specific case, the prevalidator is going to check whether a specific package is installed on this computer, pandas. The way it's going to work, first, it's going to check whether the package is installed on this computer. If yes, fine. If not, it will try to install this package on this computer. If the installation process was successful, fine. Then this execution request will be executed on this computer. If not, the background worker is going to give up. Let's see how it works. And first, let's try to call it in a synchronous mode. Of course, it executes. It doesn't try to install pandas because pandas are everywhere. It's just here for the sake of illustration. But then when we call swarm, we can look at the describe. As you can see, the execution queue size right now is 1. There are still 3 cached execution results. While we were talking, hopefully someone already took care of it. Yes, I was right. Now the execution queue is 0, and the number of cached execution results is 4. The beauty of this approach is very similar to the beauty that we witnessed during the previous demo. The more programs are connected to the same portal, the more computers are connected to the same portal, the larger the swarm of background workers, if each of which is looking for work, the bigger is the collective performance, the collective power of this virtual cluster. And again, the cluster can be as little as just one computer or as large as millions of computers. Let's see a few more examples. Pre-validator can check the amount of currently unused memory on the computer, not the amount of installed memory, but amount of memory which is going to be available for this specific piece of code to execute. And we can combine different pre-validators. We can check a number of packages installed. We can check what is the number of unused CPU cores, etc., etc. And you can figure out, the pre-validator is basically a function. You can write your own pre-validator that checks something very unique, very specific for your code. So it's that simple. There is no rocket science. Of course, it looks simple under the hood. There is a lot of complexity, but from practical standpoint, we are talking about replacing expensive and slow execution with fast and cheap storage. And when I say fast and cheap, of course, this approach is not going to work for latency-sensitive workflows. If you need millisecond time response, this is not the approach to use. But if we are talking about slow-running workflows that run for hours or days or weeks, and that are expensive because they require a lot of computers to be involved, GPUs, etc., this is where this approach is going to be beneficial. Let's go back to our presentation. We just went through the demos. As I mentioned, links to the demos are in the presentation, and the slide deck is going to be available for everyone to look after the webinar. Let's talk a little bit about functional programming in general. First of all, what is functional programming? I'm not inviting you to type your answer into chat because the answer can be very long, but at least think, what do you think is functional programming? And I realize that some people here only work with Python, and Python is not exactly functional language, even though it supports a functional paradigm. There are languages that are specifically designed to only using functional programming. But even the people who are specifically using, say, I don't know, Lisp, I'm not sure if people still use Lisp, but for example, or Haskell or whatever, oftentimes they come with different definitions of what functional programming is. The most interesting one that I saw comes from Uncle Bob. He said functional programming is programming without using assignment statement, which, if you think about it, kind of makes sense, but more as an explanation, not as a definition. When it comes to definitions, they evolved over time because it took several decades for functional programming to grow, and I hope it's going to continue to evolve. And what people understood by functional programming 20 years ago is very different from how we understand functional programming today. And I actually wrote a blog post. You can later go there and see the details of the evolution. In fact, it was not me who wrote it. It was OpenAI's O1 Pro with a little bit of editorial help from me. But the result, I believe, is very, very good and very, very interesting. But from practical standpoint, if you ask me at this point of time, what is functional programming? I would say that this is an approach to software engineering that, number one, considers functions to be first-class citizens. What does it mean? A function can be stored as inside a variable or inside a data structure. A function can be passed as an input to another function. A function can be returned as an output of as an execution result of some other function. And we can even dynamically compose functions during the runtime. So this is the cornerstone of modern practical functional programming. And then there are a few aspirational things, a few best practices. One of them we already talked a lot today, which is using pure functions. Another is using immutable data. Once you create a piece of data, you never change it. If needed, you just create a new piece of data. Encouragement to use declarative style of programming, not telling how to do something, but rather telling computer what to do. And of course, using recursion over loops. This is the famous thing when it comes to functional programming. And let's see in practice how how it works, let's go to our next demo today, the final demo. Here, I'm not going to execute it because some pieces of the code actually are going to take some time to run. I want to go fast through the demo. So let me just show you the outputs which are here. So we are creating our, importing Pythagoras. We are creating the portal. At this point of time, the portal is empty. And then we are creating our pure function. In this case, we are talking about factorial because this is a perfect example to see how recursion works. I'm not going to navigate through what is inside the function. I assume that everyone knows how it will work. And we can compute it, and we can see that the first time it runs, it takes some time to compute factorial of 50, but the second time we call it, the execution time is way faster because we are using persistent cache. Not a big deal right now, right? Textbook example of memoization for factorial. But in real world, the situation is more complex. In real world, recursion not necessarily always works. In case of factorial, let's go down. In case of factorial, if you create your recursive function using Python, in Python there is a limit for the depth of the call stack. And you can manually change this limit, but still this limit exists. And for example, if you try to compute factorial for 1,000 using recursive approach, it's going to throw an exception. And it's going to tell you, hey, you can't do it because you reached the maximum recursion depth. Doesn't really matter whether this is a code written with no decorators, with no memoization, or code written with memoization. Still, there is recursion depth here. We can play with it. Say first we call factorial for 50, then for 100, then for 150. And in this case, memoization will help. But this defeats the idea of using beautiful recursion. And the same problem is going to happen if you're using a pure decorator as well. Why? Because inside the decorator, there is still the same Python code. There is still all the limitations that Python has. They all apply. But someone just posted a comment. To understand recursion, you need first to understand recursion. That's exactly the point. I completely agree with that. And you see, actually dumped pretty large number of errors. Let's go down. But Pythagoras is smart enough. We can tell Pythagoras, hey, this specific parameter is a recursive parameter. In this case, under the hood, it's going to do a lot of optimizations. And the next time you call your recursive function, it doesn't really matter what is the limit of the call stack. The function is going to work. And here we are computing a factorial for 1,000. It takes a little bit more time, as you can see, because, well, it has to apply all those smart optimizations. But yet, at the end, we have the factorial for 1,000 computed, which is a pretty large number. I have no idea how many digits are here. And if you look at the portal inside, it stored all the intermediate results, the factorial for 99, 75, 350, whatever. And it also stored a lot of other intermediate results. So the next time someone needs to use a factorial, it's going to be available immediately. Another example, classical example from functional programming is doing maps. We create a function that takes a list and another function as inputs, and applies that other function to each of the elements of the list. And we can use it here with Pythagoras, with this decorator pure. You can see the examples. But the beauty here that now we can benefit from all the optimizations that come with persistent memoization and deterministic parallelization. So if the transformer function is long and expensive, here we can get huge performance gain in terms of cost and time of executing this workflow. But we can take it a step further. There is this thing called fix an argument, which means for a pure function, that has several inputs, we can bind one or a few of the inputs to some specific values, and that would allow us to create a new function. And in this case, we create a new function, mySquareMap, that takes as an input only a list and applies this mySquare function which we defined before. So we composed a new function from the existing one by decreasing the number of inputs, by binding some of the inputs. And that's very, very classical thing for functional programming. And here, of course, there is additional restriction, which is a function has to be self-contained. Remember, we don't know where it's going to be executed, so it has to be autonomous. How do we do it in case when we have a few mutually recursive functions? Well, if you have a little bit of time and if you want to think how a little bit of more challenging problems are solved using this approach, you can later take a look at this example that shows how is even and is odd are implemented using this approach, so we can still benefit from persistent memoization and deterministic parallelization while using functions that depend from each other. So they're supposed to be autonomous, yet they're dependent from each other. How do you address it? Well, here's an example. You can take this example later. That was the third demo, very short. And now let's talk how functional programming could evolve in the future. I can think of two major additions to the current functional programming. Let's think of functional programming 2.0. The first one is planet scale execution model, because I believe the biggest benefits are coming from using those large portals. Yes, from practical standpoint, for now we're talking about enterprise, but in the future, hopefully, we will be talking about the planet. And when the entire planet serves as huge supercomputer and huge super cache that can store all the intermediate execution results ever created by the civilization, and that can parallelize execution for the new code that was not being executed before, but once it is executed, again, it's stored in this cache. That is going to create amazing, amazing benefits for us. Think of what kind of problems we can solve. We can faster get to, I don't know, developing cure of cancer. We can faster get to AGI, whatever it means. We can faster get to designing starships that would, or spaceships that would get us to new galaxies, etc., etc. So the first thing is, let's use this collective power, this huge amount of devices and efficient devices that we have in an efficient way. For that, we need to have this planet scale execution model. The second development comes as basically the consequence of the first. All those computers are different. So we need to have, and the amount of code is huge, right? So we need to have a way to execute different versions of the same code on different computers. Number one, it means code multi-versioning, a coexistence of many alternative versions of the same code and co-execution if needed. And number two, specifically, I would like to pay attention to what I call protected execution, which means we need to protect a computer. When a computer runs some code that someone else created, we need to make sure that this code doesn't make any harm for the computer when executed, doesn't delete anything, etc. But we also need to make sure that the computer doesn't cheat. And when the computer returns some result and says, hey, this is the result of the execution, for this, we need to have a way to validate that the result was correct. And there is a number of tools for this. For example, the post-validators that are doing the basic checks, or the code isolation that we can apply to our functions when they execute, etc., etc. I'm not going to talk about the implementation details here. What I'm going to talk is just to address that, hey, this is important. And also the important part is content undersea. When I started programming, I guess one of my first languages was C and then C++. And then C and C++, each value has an address. And an address is basically an offset in memory. When we are talking about global execution model, there is no way we can use offset in memory. We need to have a different way of addressing, which is content-based addressing, which is using a hash of a value as its address. In fact, it's more advanced. It's not just hash. From practical standpoint, it has to be more complex. But the core idea is very simple. the value itself allows us to define the address, and it has nothing to do with where physically this value is stored. So this is where I see the functional programming is going to evolve, and hopefully many of us participating here today at this webinar are going to contribute to this evolution. And from practical standpoint, if you want to contribute to this evolution, I encourage you to play with Pythagoras. It's a research preview. I'm not saying it's production ready, but it's experimentation ready. And maybe for some use cases, it's actually going to work for you even as it is right now. But obviously, I hope it will evolve, and I hope. So far, I've been basically the only person writing code. It's pretty large project. Under the hood, there are many. It's pretty complex. It seems to be very easy to use, but the reason it's easy to use is because there is a lot of happening under the hood. But I hope that over time there will be a community that will be working on this project or similar projects, and we will move forward the entire world of functional programming. And there are two ways how you can contribute and how you can benefit. If you think that for your workflows, this is something that can create value, please reach out to me, and we can chat, and I can suggest you how to use Pythagoras as it is, or maybe I can add some additional features to it. Or if you want to contribute, it's an open source project. I encourage everyone to participate. Again, reach out to me. There is huge amount of stuff that needs to be done, and everyone is welcome to help. The best way to reach out to me is to use LinkedIn. Please send me a connection request. I'm going to accept your request, and then we can chat on LinkedIn. This is the best way to interact. With that in mind, thank you so much for your time. Thank you so much for participating. We started a little bit late, so I'm not entirely sure whether we still have time for questions, but we can try. And Sharice promised to help me with the questions.
Yeah, so there are a few questions right now. I'll start with some of the first ones. Igor would like to know, when a function caches the result for every unique input, how can one effectively manage the cache size if the number of potential inputs is vast or unbounded?
Well, the answer I'm going to give is probably not the answer that Igor expects. I don't think we should manage this size. I think we should plan for this size to be ever increasing, because this is the idea. Compute once, reuse forever. So if we decide to evict some values which are not frequently used, etc., we are going to kill significant part of the benefits here. So the trade-off which is happening here, yes, we are replacing expensive compute with cheap storage, but we need a lot of that storage. So my opinionated opinion, oh my God, that's a terrible phrase. My thinking here is that we need to explicitly decide to plan for huge storage. And the best case here is, of course, S3. Services like S3, which are theoretically unlimited. From practical standpoint, there is no limit. And they're cheap.
So there's actually a couple of questions regarding storage. Let's go with, sorry, I just had it. So Stas Kerman asked, as far as speed, permanent storage access is often relatively slow. How do you solve this problem?
First of all, Stas, thank you for coming. I greatly enjoyed SWOT conferences, which I used to attend when I lived in Silicon Valley. Thank you for doing those. I hope you still organize them. There are two things here. Number one, as I mentioned, this specific approach is not for latency sensitive workflows. So if you need fast response, probably you need something different. Now, depending on what is fastest response, we can think of several different strategies how to address it if we still want to use this approach. One is just a different deployment strategy. For example, if we want to work really fast, S3 is not always the best option. But using, if you're using Amazon, using elastic file service, file system from Amazon, AWS EFS, and deploying all your computers in one VPC and connecting them to this, that by itself is going to make it super, super fast. We can take it even a step further, and we can say, hey, there are different ways to create storage. Remember, the backend is just storage, but for example, Redis is also storage. Redis stands for remote dictionary, right? It's just a key value store. We can easily create a portal. Well, not easily, it's not right now in the system, but we can easily extend the system to support portals based on Redis. That by itself is going to make it super, super fast. But still, in this case, we are losing the main benefit, which is, well, Redis is not cheap storage, right? It's very expensive storage, and you need to run those servers somewhere. It's not, and yes, you can make it persistent, but that is going to make it even more expensive. So there are trade-offs here, depending on the specific need, depending on the specific use case. There are different approaches how to address it. But the main use case is the slow-running, expensive workflows that are running for days and hours, and maybe even weeks. And for them, latency doesn't matter.
Okay, so then we have another question from Anonymous. No, actually, let's do the Miss M's question. How is the security implication in sharing your cache?
It depends on what exactly do we mean by security implications. So there are several ways to look at security here. Number one, sharing the cache. Number two, executing the code that someone else wrote. And there are different ways to think of it and address it. First of all, if you share your cache, if someone doesn't have the inputs you have for your function, and someone doesn't have exactly the same function, there is no way for this someone to know the address of the output, because it's a cryptographic hash. So if they don't have exactly the same data points that you had, there is no way they will generate the same address. But if they do have the same function, and they do have the same inputs for this function, of course, they can easily generate the address of the future result and get access to this address. But I'm sorry, in this case, they can also execute the function with the same inputs and get the result anyway. So from that perspective, it's for those people who don't have the exact same thing that you have, it's going to be very hard, not impossible, but very hard to access the data. But as I said, I understand that at this point of time, the world is not ready to put in everything in one place and sharing your portal with everyone. And the same way as with GitHub, you can share some of your repositories with the world, and yet you can keep some of other repositories private. The same here. Under the hood, you can actually create several different portals, and you can say the results of caching these functions, they go to this portal, and those functions, they cached to that portal. And you can make some of the portals publicly available, so everyone will benefit from using them. And you can keep some others private to your company or to your team, or even to personally just you. So if there is something super important, it will never be shared. So there are different ways to address it. From practical standpoint, work with multiple portals is the most it's probably the best approach as of now. Maybe in the future there will be other approaches.
So also regarding portals, somebody would like to know if they create a portal in their computer's file system, for example, a folder in their home directory, they would like to know if it would be persisted even after they turn off their machine.
Assuming that the hard drive is not going to die after they turn off the machine. Yes, it's in the hard drive, right? It's in the folder on your machine. So you restart your computer, it's still there on the hard drive, unless you disconnect your hard drive, or unless your computer dies, which actually happened to my laptop yesterday, like literally yesterday. So yes, stuff happens. This is why the basic suggestion is to if you're working on it as a student or as an individual, maybe you don't need complex setup, but just use a folder shared through Dropbox with another computer of yours or maybe with your friends. And this way you can parallelize by creating a cluster of 10 computers from your friends from your dorm, and that itself is going to be beneficial. But of course, from the production standpoint, we are talking about more advanced deployment scenarios like EFS that I keep mentioning today.
So there's also another question from Dimitro, and they would like to know if the main advantage of, I believe this was your first example, is that caching is clearly demonstrating persistent memoization.
Well, that's the definition of persistent memoization, a cache that survives restart of your program. So basically, caching is super beneficial, frequently used technology. We are just taking it to the next level. Number one, we make it persistent. Number one, we make it distributed. Number two,
and then regarding functions, somebody would like to know that if they have a function with some parameters, and then later they create a new function with a new name, but the same parameters and body, or with the same but another set of parameters, what would happen?
well,
Which thing would run?
I'm not entirely sure. So first question, another name. Another name means another source code. Pythagoras is smart enough, but not that smart. If you change the name, probably there was a reason. It's going to trust you that there was a reason why you did it. So everything will have to be recomputed. If the original function was really expensive, the best way to approach it, if you really need a new name, is just to create a wrapper function with a new name. Now, if you're talking about different parameters, I'm not sure I understand the use case, because if the inputs are different, probably what happens inside should also be different. It should account for those new inputs. So from that perspective, if it's just cosmetic change for the sake of making code more readable, my recommendation would be, again, just create a wrapper function so you can reuse the cache.
Okay, and then we have one of the older questions, which was that the session title was about faster ML. They wanted to know how Pythagoras can be applied, and they were wondering if it's useful more so for data preparation than for training.
I think we can talk about different stages in the AI/ML life cycle. It starts, of course, with data preparation, but then we are talking about experimenting with architecture. And oftentimes, when we are playing with a new architecture, the components inside could be very much the same, just the overall model is different. And in fact, there are even specific architectures designed to benefit from caching, just traditional caching. But those specific architectures can easily be used here. Now, the next thing, once you picked the best architecture, you start working with hyperparameter optimization. This is crazily expensive process, but again, oftentimes there are redundancies when you're doing whatever grid search or whatever approach you use to hyperparameter optimization. Oftentimes there are just a few parameters change, some others staying the same, so a significant part of the code doesn't change at all. The inputs are exactly the same. You don't need to recompute those. So for hyperparameter optimization, this is super efficient. And of course, it's super efficient even if there is no overlap in execution, because you can easily parallelize. Speaking of hyperparameter optimization, you can have, I don't know, millions of alternatives that you want to check. You can easily use this approach. And then, of course, when it comes to actual data, actual inference, it's going to be a bit, or maybe not a bit, less efficient. The hit rate is going to be smaller, but still it's going to accelerate at least some of the workflows, and it's going to accelerate it on the basic level. If, say, there is the same input, the same prompt, then you get the same output. You can play creatively here. For example, we can vectorize the input, get the embeddings, decrease the precision of those embeddings, which by itself is a technique used in ML to generalize generalization. But then when you increase the precision in the embedding factor, you can actually get several alternative prompts that are considered to be the same. Or we can take it even further. Say a library I'm working right now from kind of a main job perspective is working with several alternative models, given prompt to them, and then somehow combining their result to get better result. And that itself, if you think about it, there are so many different ways to work with it. I'm not sure if many people here are familiar with it, but there is this technique called prompt consistency, when you're raising the temperature for your LLM high, and you're given the same prompt many, many times to the same LLM, and you're getting different results, and then you pick the most frequent one as the best one. Then there is the universal self-consistency, when we are talking about more advanced ways to pick the best results. But the core idea is you are given the same prompt to the same model many times, or maybe you are lowering down the temperature, but you're changing the seed all the time. If we extend this idea to using several LLMs, the number of times you call the API is going to be huge. It's going to be quite expensive. So let's say you're using this approach to pick the best result and maybe train your model when you're using your model, right? Your thing, when you're using several different models, you're using this self-consistency approach. So you're calling API for each model many, many times. Then you use the same models in the model using this LLM as a judge approach to pick the best result. And over time, you consistently see that the best result is generated by just one model. So what you do, you stop doing this expensive process, right? You just pick one model, which is the best. But then Elon Musk comes with Grok, which was not on the leaderboards before. And apparently there is new model that you need to experiment and play back. You need to repeat the entire process. So if your results are cached, this addition of new model to the entire ensemble of the models is going to be very simple, very cheap. But then you can run the entire evaluation cycle very fast again, and it's going to be super cheap. But if you didn't have this persistent memoization approach, then it would be super, super expensive. So even with this kind of strategies, this is super beneficial. But of course, we are talking about different specific workflows, different specific use cases, different specific strategies. And depending on what exactly you're doing, is it traditional machine learning, is it large language models or large multimodal models, what kind of architectures, what kind of process, there are different places where it can benefit you. And there are places where maybe there are some workflows that are not going to benefit from it. It's also quite possible. I'm not saying it's a universal solution. Not at all. There are no silver bullets.
Well,
okay.
It looks like that's it.
Yeah, we took a little bit longer than expected. Once again, thank you so much to everyone who joined us. If you think that you can benefit from this approach, or if you think that you can contribute to developing this, please send me a LinkedIn invite. Or just if you participated in the webinar today, send me a LinkedIn invite. LinkedIn invite. I would like to stay in touch with you guys. And if you think that this is something beneficial to you, just let me know what is your workflow. We can chat how we can help you. If you want to be part of the open source group that is working on this project, also you're very, very, very welcome. And of course, great thank you for joining, and thank you, Sharice, for being our MC today, our host. And of course, thank you to Dimas Fedorets and Data Phoenix for hosting this webinar.
Thank you everyone so much for joining.